Hello everyone, welcome to this online course on material science. This is lecture 14 in the module 1 on magnetism. If you recall, in the last lecture I started discussing this Langevin model of paramagnetism, and I'm following this book, Magnetism in Condensed Matter by Stephen Blundell. I believe the contents can be found in chapter 2. So during the discussion of the Langevin model, we have an intuitive picture in our mind that we have a piece of solid, and inside that solid we have a number of ions or atoms, right? And every ions and atoms has some magnetic dipole moment, mu, let's say here, right? And they can be directed in any direction in the three-dimensional space. So to cover all the direction, we were considering some sphere of unit radius, right? And we are considering those moments which lie in this annulus first, right? And we say this annulus will give us the solid angle contribution, which is nothing but half sine theta d theta, right? And the polar angle is z, and we are applying the magnetic field also along z direction. So any magnetic moment in this ring is making an angle theta with z, right? Or b, the same thing, right? So if you ask what is the z component of the magnetic dipole moment, let's say we have some moment pointing in this direction, the angle is theta. So along z, this is nothing but the value times the cosine of the angle between mu and z, right? That's our z component. And then we came across the term, the energy of the magnetic dipole moment, which is nothing but minus mu b cos theta, right? And then we talked about this Boltzmann factor, right? The Boltzmann factor, which is exponentiation of minus energy divided by Boltzmann constant times the temperature, right? And if you put the value of E, we showed that this Boltzmann factor is nothing but exponent, and this minus sign get cancelled. We have mu b cos theta divided by kBt, right? So that's our Boltzmann factor. And then I said that with these notations and with these quantities, we can calculate the expectation value of the z component of the angular momentum. And then I say it's a ratio where you, in the denominator, you integrate out over the solid angle the Boltzmann weight, right? So weight is, so this quantity is called Boltzmann weight, Boltzmann factor, many names, but same quantity. And on the numerator, we have mu z times the weight, which is mu b cosine theta by kBt, and you're integrating over the whole solid angle, right? So we have a numerator and the denominator. We need to evaluate this quantity, right? So let me evaluate this quantity first, right? And let's do it over here. So on the denominator, we have integration over the angle of the Boltzmann factor, right? The Boltzmann factor is mu b cosine theta divided by kBt, right? And we have solid angle, and we know what is the value of solid angle. That's nothing but half sine theta d theta, right? So we need to perform this integration over the theta variable, and from your geometry basics, you know theta is the angle between the z-axis and your moment, right? That's your polar angle. So theta has a range which starts from 0 to pi, right? So we need to perform this integration from 0 to pi. So from this sort of integration, the idea is you need some replacement of variable. So we will assume that cosine theta is x, then dx is nothing but sine theta d theta, right? And change of variables. So when theta is pi, x is -1, and when theta is 0, x is 1, right? So you need to change these variables into x and put the limits. So then this integration, right, you can see this integration becomes, so we have some half, we have some minus, and then the upper limit, the lower limit is +1, upper limit is -1, and cos theta is x, and we are assuming mu b by kbt, that's a fixed quantity in this problem. It's nothing but some y which is not varying over x, and then sine theta d is just dx, right? So that's the integration we need to perform. So y is nothing but mu b divided by kbt. Okay, now how do you perform this integration? That's very easy. Let me change the limit first by eliminating this minus sign. So now it's -1 to +1. That's e to the power xy dx, and so the integration is nothing but e to the power xy divided by y, and then we need to put the limit -1 to +1. The result is half 1 by y e to the power y minus e to the power minus y. Just put the limit for the x. So that's the value for the denominator, right? Now we need to find out the value of the numerator. And what we have in the numerator, we have this quantity, right? So let's just copy it and evaluate the expressions. On the numerator, we have the integration of mu z times the Boltzmann factor, right? And the factor is nothing but mu b cos theta divided by kbt, and we are integrating over the solid angle, which is nothing but half sine theta d theta, and the limit is 0 to pi for the theta, right? You know what is the value of mu z, so put the value of mu z first. So that's like mu cos theta. So mu is just a fixed number. It's going out of the integration, and inside the integration we have cos theta, then the factor, which is the Boltzmann factor, cos theta divided by kbt, and then sine theta d theta, bring out the half, right? We have some half factor here. Same substitution we need to use, right? We will put x is equal to cos theta, and then you can see this, just do it as a homework. The result from this will be mu by 2, limit be -1 to +1. Now we have some cos theta here, and on the exponent we will have xy dx. Just put the variable x is equal to cos theta, right? And perform some substitution. It should be very easy. So we need to perform this integration. This is like a 2 function. So we will use the integration of parts to evaluate this integration. Let's do it here. So we have some mu by 2, and this is our first function, and this is our second function. So you remember that the rule is you keep the first function, but then integrate the second function, right? So which is e to the power xy. This is the integration of this function, and then you put the limit -1 to +1, right? Now then minus integration of the, then first function should be differentiated with respect to x, that's 1, and second function needs to be integrated, that's like xy by y, right? And then we need to put dx here. That's our integration, right? So if you look at this quantity, what is that? That's like e to the power y minus e to the power minus y, right? And you are getting a plus because there is a minus sign here, and x is minus by, right? That's all right. So by y, that's this quantity. So make it bigger bracket here. And about what about this? So 1 by y goes out, and the integration of e to the power xy dx, which is nothing but e to the power xy by y, and the limit -1 to +1, right? And then close the curly bracket. So we have two terms in this integration, right? One is here, and once you put the limit, you will have 1 by y square, and then you need to put the limit, right? So let me write the expression here, mu by 2, and then here I will have e to the power y, sorry, and then plus e to the power -y divided by y, and here I will have 1 by y square e to the power y minus e to the power -y. Just put the limit in the previous expression and you will find this result easily. So that's the result of the numerator, and we know what is the denominator, right? You have, I hope you have it on your somewhere written. So let's now find out the value of the expectation value, right? We know what is the numerator and what is the denominator. Let's put the value here. So on the numerator, we have this quantity. Yeah, minus 1 by mu square to the minus y, right? And on the denominator, we have, I believe, half and e to the power y minus e to the power -y, if I'm not wrong, right? So the question is, what to do next? You just do some, like you just divide this expression from here. So you're dividing this quantity minus this quantity, right? So we have two terms there. Half gets cancelled. We have some mu. So let me write it out. E to the power ey, e to the power -ey divided by, that's one term, divided by, we have also a y, right? I forgot to press y. So this y get cancelled, but we have extra y here, but these two cancel each other, right? So this is our expression. And if you remember from your trigonometric expression, this is can be written as cot hyperbolic, right? So mu times cot hyperbolic y minus 1 by y. And this function, cot hyperbolic y minus 1 by y, is famously known as the Langevin function, right? You will see in the textbook, people write it like L times y. What is L? L is the Langevin function. So that's our Langevin function. Now on the left, you have mu z, right? So let me make a couple of comments about this expression. We will plot the expression in the next lecture, but let me express in these quantities in terms of something measurable, right? For example, let us assume there is a term which is known as saturization magnetization, right? So saturization magnetization. So what is this quantity? This is the amount of magnetization occurs when every moment in your solid aligns, every moment aligns with your magnetic field. That's the maximum saturation, right? So that's the maximum value of the magnetic field you can get in response of some magnetic field. That's your saturation magnetization, and this quantity, we are assuming that we have some dipole moment per atom or per ion is like that, and N is the number of atoms per unit volume, right? So that's the saturation magnetization, is if they just add up, right? Every mu adds up because they are aligned. So usually the small n represents the number of ions per unit volume times the magnetic moment of each atom, right? That's your saturation magnetization. And what is the magnetization that we often get when the magnetic field is not too high? Then you just get the expectation value of what we have calculated, right, from each of your atoms. So if you look now, the ratio of m and ms is the same as mu z times b, right? So this is same as m by ms. this is an important relation. We will draw this expression, and then we will see how the Curie paramagnetism comes out from this expression. But the important point to remember is that the paramagnetic magnetization follows a Langevin function in the classical model, right? And the Langevin function is given by cot hyperbolic y minus 1 by y. And we will see how this model gets modified when we add quantum mechanical consideration. You will see this function will be changed, right? But the point to remember here is that the saturation magnetization is something that in high magnetic field, when you have all the moments aligned, that's the maximum magnetic field, magnetization you can get from that piece of solid, right? And the ratio of the magnetization to that ms is given by this Langevin function. I think that's about it, and thanks for listening.